Let's begin. You saw my announcement. Probably if you haven't, check your Canvas announcements about the plan for the rest of the semester. The first elephant in the room was exam 2, which was tentatively set at on November 7th. Obviously, that's unrealistic and not true. And you have other exams as well. For some reason, everyone expects me to change my exam to accommodate the other courses, and that's fine. You know, I'm very flexible that way and happy to do that. So I moved, it's unrealistic to do it on November 7th. It will occur on November 19th. Okay, so that gives us plenty of time to finish with regression, get the homework moving, and we will be ready for exam 2. Obviously, we are running a little late this semester because it's a different semester compared to the spring semester. So it's an unfair comparison. In the spring, the group is typically more prepared for Python stuff, has seen some other material in courses, and I can go faster, I can cover more topics. When you move numerical methods to the fall, you have to move a little slower, take a slower pace. I still would like, and I intend on covering the vast majority of the material I cover normally. Except from here onwards, I want to go a little faster and slightly compress the lectures without sacrificing significant material. So instead of doing 7 examples on arbitrary basis function regressions, I'll do 3, and the other 4 you can do them at home. Okay, if there's a silly little activity doing the regression in Python with our own linear system versus using Polyfit, we'll pick one of them. We'll do the one with Polyfit because that's in practice the one you will use later, and then let you do the other activity at home. So that alone saves 15 minutes, that one activity or the other example. So I'm hoping to, instead of doing 4 lectures on regression, I do them in 3 and combine numerical calculus into 1 lecture. So that's numerical integration and numerical differentiation. So that's the expectation here. There's some activities where I'm going to tell you, okay, don't do this activity. Pretend you go and try it at home. I'll just give you the answer here, explain it a little bit, but go and repeat it at home and re-engage with us. But regardless whether we do them in class or not, you have to repeat those activities because sometimes you don't even get to do them correctly in class. So you have to repeat them anyway. So you might as well just repeat them at home so that you're ready. Okay. So we're working with regression now, and regression is a highly sophisticated approach to representing data that you measure in real life. And unlike interpolation, where interpolation works by weaving a curve that represents the data, but it weaves it through each and every point that is presented to you. And normally you use interpolation for really clean, well-structured data that typically corresponds to a physical law. Like, for example, the density versus temperature. There's a one-to-one correspondence. There's a direct dependence of the density on temperature, and you can see a nice clean trend. Whereas the height versus femur, there's a lot of variability there. And obviously, the height of a person is not only dependent on the femur length, it's a correlation between the two. The height of the person is dependent on nutrition, genetics, a bunch of other things, environment, and so on. And so you'll see the data there. When you present the data for height versus femur, you're going to see it scattered over the place like we saw last time. It's not nice and clean. I'll show you that plot again. It's not nice and clean, belonging on one line. There's for one single femur height, femur length, you have 2 heights, for example, here, or here, right? So because that data is not, it's realistic data, it's not clean like you would think about density and temperature. So in this case, this is a clear case for regression rather than interpolation. Now regression, what it does, it elevates the concept of representing the data and says instead of capturing the data exactly and recovering it exactly, because the data anyway has uncertainty on it and we don't know it exactly, let's just capture the trend of the data. Since we're approximating, we have uncertainty anywhere, let's just capture the trend of the data. And that's the basic idea of this regression. So in this chapter, you will learn a lot of cool things that will get you ready to do data science. That's the ultimate objective of of this and kind of hopefully the series with statistics that would lead you to become ready to do data science in the future. You'll be able to conduct full least squares regression analysis, and we will learn what we mean by least squares and specifically why that's the most useful type of regression. There are other kinds of regression we could do. So regression now, think of the word regression as capturing the trend of a data. You can do it with least squares, you can do it with other approaches, and you will learn about all of that. And given a set of observations and a model curve with unknown parameters, so the model curve could be a straight line, could be a cubic, could be sinusoidal. That's the you want to model the data with a curve like that. Then your objective is to find the parameters, and you will minimize the square of the error. So that's where the word least squares. Least means the minimum. You will minimize the square of the error between the model and the observations. We'll get into all the details for that. Define what we mean by linear regression. Define what we mean by least squares regression. Formulate the governing equations for linear regression with arbitrary basis functions using the least squares derivation. We will call those the normal equations. Define and compute the R squared, the mean, standard deviation, standard error, and the coefficient of determination. The R squared value that you've probably seen if you did data in high school in Excel or something, say, oh, you know, press get a trend line, and the R squared value is 90%, so this is good. The higher the R squared value, the better. We'll understand why that is from an error perspective and a statistical perspective. So this is like really seeding some thought for your statistics course in the spring. Visually identify which set of data has a higher standard deviation than another. It's a really simple concept. Visually identify from a set of data if regression will result in a high R squared value or a low one. So I'll give you a set of data and tell you, okay, regress this. Do you think you're going to get a high R squared value or not? You'll be able to just spot that but just by learning what the R squared value is. We'll create code in Python for linear regression. We'll define what the normal equations are, which are the governing equations I mentioned earlier. Use the linear version of the normal equation and the transpose method to formulate generalized regression with arbitrary basis functions. This is like the cream of linear regression. And you will learn very quickly that what I mean by linear regression is not regression to a straight line. What I mean by linear regression is the same thing I meant by linear interpolation, is that the parameters show up linearly in the model equations. Okay? So regression to a cubic is going to be still a linear regression problem. Formulate the equations for nonlinear regression, solve nonlinear regression problems using Newton's method. So, you know, we circle back to linear systems and nonlinear systems. And finally, convert certain nonlinear models into linear regression analysis. Very powerful tool. Okay, let's start. Here's the basic idea of regression. You are given some input data. Think of the y-axis as the dependent variable, density versus temperature, or person's height versus femur. And on the x-axis, you put the independent variable, so response versus the causative variable. And each one of those data points, we call that the input data. Those are our input data. We want to put a model curve. We think that this data follows a trend like this, or you might think it goes by a straight line. Whatever you think it is, you want to put this model curve in between. A line is still a curve, a straight line is still a curve. And you want to put it between those data, and you want to fit the model curve that captures the trend of the data. But how do we do that? I mean, it's nice and rosy. Like, yeah, we're going to fit a model curve that captures the trend of the data. How do you do that technically? How do I get this model equation? How do I get this model curve? How do I get the coefficients, etc. for it? We will first learn to do basic regression in Python, and then we'll get into the mechanics of it. So I want to teach you how to drive first, so you can enjoy, you know, racing with this and have fun with the car, and then we will learn how the engine works and how the transmission works. You already used this approach in Python when we did interpolation. Remember Polyfit? When we did Polyfit for interpolation to high-order polynomials. And I told you that if you use degree, so for n plus 1 points with interpolation, you could fit a polynomial of order n. And if you remember, I told you with Polyfit, if you use anything less than n, it becomes regression. Go back to the interpolation slides. If you use any value less than n, it becomes regression. Why? Because then you have less coefficients than there are points. So say you have 10 points and you want to fit a polynomial of order 3. Well, the polynomial of order 3 has 4 unknowns, but you have 10 points. How can you match those conditions? It's an overdetermined system. Regression will do that for you. It will allow you to put a straight line among 10 points or a cubic among 100 points. Okay? So when you use the degree, so in Polyfit, the same thing that we used last time, but instead of using n for the degree, and if you have n plus 1 points, don't use n, you use the actual model you want to regress to, then you get what's called regression. Very simple. So we already used Polyfit, we already used Polyval. If you need a refresher, you can read through those or go back to the other lecture. The point is, if you put degree equal 1, then you will do a regression to a straight line. If you put degree equal 2, you do a regression to a quadratic, which looks like this. And if you put degree equal 3, you get regression to a cubic, and so on and so forth. Okay, so you could have 1,000 points and put degree 1, it will do a regression to a straight line. Whether it's a successful, good regression or not, that's a different question. But this will do it for you. And so for n plus 1 points, this slide is taken exactly out of the interpolation slide. For n plus 1 points, if you choose a degree less than n, then regression will be performed, and that's exactly what we want to do here. So here's our first coding activity. You know, we could say, okay, this is regression, you're done, go home, but we're gonna dig deeper, okay? But the first activity is just to know how to do a regression in Python. So we get that out of the way. You have the tool to use it. In your projects or whatever, you know how to do regression very quickly and simply with Python. So we're going to do this first coding activity. We're going to use Polyfit to regress the height versus femur data. So I already showed you the slides, already showed you the answer. The answer was like x plus 1, y equal, height is equal, person's height is equal femur length plus 123.7 or something. So we're going to use Polyfit to deduce that equation. We already have the height versus femur data inside this regression activity 1, height versus femur notebook with gaps on Canvas. So go on Canvas. You can go on modules. On the left menu, there's regression, a regression module. And in there, you can find this regression activity notebook. Download it. Let's work on it together. And we will do regression on the height versus femur data. Just for reference, I want to remind you of the equation. So the equation we got here was x plus 123.2. So this was done, I think, using Excel or something. I don't remember. Maybe the built-in tool in Keynote. So this is what we expect to get. I expect to get something like this equation. Right, so get that notebook, download it, please. And let's get our first regression. Again, I'm teaching you how to drive first, and then we will learn how the engine works. Okay, so regression with gaps. I have it here. Okay, so I'm going to move this notebook over here. So this is what you should see if you download this, this notebook. If you download this notebook, and I will move my slides. If you don't remember what Polyfit does, I will move it over here. So if you start working through this notebook, you'll notice I got a bunch of information here. First example, I got the x and y data, so the independent and dependent variable. And we get the boilerplate, etc. And obviously, I need to import Polyfit and Polyval to do the regression and the evaluation of the model. You hopefully should know this by now. And then I'm going to put the data in NumPy arrays, so the xi data and the yi data from now on, just like we did with interpolation. X input, y input, I stands for input. All my variables, I'm going to call them xi, yi, just for simplicity. Independent and dependent variable. So the independent variable is the femur length, and the dependent variable will be the person's height. First thing you do is you plot the data, and you give it some labels, right? So this is an adequate plot, what I would expect from you in the homework, for example. Title, height versus femur, person's height in centimeters versus femur length. So that's exactly the data that I I think, a subset or a superset of it, the one I showed in the slides. But this is the data, and we want to regress that to a straight line. Okay? So that's your assignment now, regression to a straight line using Polyfit. We can use NumPy's Polyfit to perform regression in general. For regression to a straight line, you set degree equal 1. Okay? So there you go. Go ahead and try to do this based on what you know on Polyfit, for Polyfit, and see what you get. So if you don't remember, Polyfit takes at least 3 arguments, xi, yi, and degree, and I kind of named them that way for you. If you don't know what you're doing here, remember interpolation. You did this with interpolation, except for degree, you put the order of the polynomial, which is equivalent to the number of points minus 1. Over here, we're going to violate that. We're not putting n for the degree of the polynomial. We're choosing our own number, which is not consistent with the number of points. And that will result in regression. Okay, so what would be the first argument? Put data, input independent variable, and then yi for the dependent variable. For degree, I give you the answer here. You should put 1. And then the result of Polyfit is a set of coefficients. If you don't remember that, remember it, work through it in the homework, or look at the function signature, what it returns to you. If you scroll the function signature, returns polynomial coefficients as an ND array, NumPy array, containing the polynomial coefficients with the highest power first. Okay? So these are the, if you plot this, you get 1.004 or 1 times x plus 123.2, which is almost identical to what I got here, which is x plus 123.2, right? So this is, these coefficients, they start in reverse order. So this is the coefficient of the highest degree. This is the next highest degree, and so on. Because this is degree 1, so this would be the coefficient of x, and this would be the intercept, the coefficient of x to the power 0. Okay? So the result of this is that the regression line looks like 1 times x plus 123.2. Okay? So these coefficients are not in the abstract or in the blend. They mean something. Okay? The equation for the straight line is what? That's the question I just asked. So the equation for the straight line would be okay, so let's make this text. The equation for the straight line would be y is equal 1.004x plus 123.2077. Okay, I don't need that many significant figures, but okay, so that would be, so now this is your model for the data. So you can use this to make judgments, predictions about the data. Okay? So now evaluate the height of the person if the femur length is 42 centimeters. So we use polyval. What does polyval take? In the first slot, polyval takes the coefficients. In the next argument, polyval takes the value or the values you want to evaluate at. Okay? So I'm going to put coefs here. And over here, I'm going to put 42. And if I evaluate this, it gives me 165.4 centimeters. Okay? So what, if you remember your femur length you measured last time, you can plug it in here. So this polyval is equivalent to evaluating this formula at x equal 42. Agreed? That's what it's doing. It's really neat and nice because you don't, if you didn't have polyval, you have to write a Python routine that evaluates this formula every time you want and call it every time you want to evaluate a person's height based on femur length. Okay? All right, so according to our regression analysis, the perfect femur length is 165.4 centimeters tall. Okay, next I want to plot the regressed line on top of the original data. So I'm going to take the original data and plot them as a scatter in red. And then I'm going to plot the original data, but so I can create a lens space if you want. You can create a lens space here. But because this is a straight line, I don't need a linear space. I can plot it with the original input data. Okay, so here I want to plot the regression line. Y versus xi. So the xi's are here. What should I put here? Oh, I thought you had a suggestion. Daxton.
Polyval for all of your...
Bravo, thank you. Polyval, coefs, xi. Guys, polyval evaluates the regression curve, evaluates that straight line. So here I want to plot my regression line. So I want to plot 1.004x plus 123.2077 for each one of those xi's. But Polyval does just that for you. You just give it the coefficients and all of the xi's. Okay? And you plot it, and it gives you an error. Pardon me? Oh, thank you. Yes, thank you. All right, there you go. Now this looks like regression. It's not interpolation. Why? Doesn't go through each and every point. It definitely is not interpolation. This is regression. Now there's a cool thing you can do with regression. With interpolation, you get in trouble if you go outside the range of points you're given. When we're doing density versus temperature, temperature was between 100 and 1,000, you do interpolation. If you even go to 1,001, you might get a completely unrealistic value. Because you're going outside the bounds of your data, that becomes extrapolation. We didn't cover that. Interpolation only does between interpoints, okay? Regression allows you to make a prediction. You can go outside the data because the regression curve claimed to capture the trend of the data. It never claimed to recover the data exactly. I'm capturing the trend. I can go outside the bounds, and I will still make a darn good prediction. So with regression, you can make predictions outside the bounds of your data. Okay? So that's a cool feature about regression. Okay. Now you know how to drive. And again, I said I'm going to go a little faster pace, because we covered Polyfit. You know, you just did the homework for that. Don't remember it. Go back, redo it. This tool, Polyfit, you should know it by heart from now until the end of life, until something other than Python comes up. And they'll probably call it Polyfit because of backwards compatibility. Okay? But those are things that you should have. You should know that if I want to interpolate or regress, I go to Polyfit. We're going to learn another thing called CurveFit. Also go to that. fsolve, it's one thing that you always have to go to. Matplotlib, plt.plot, you always go to those. So those need to be in your glossary, in your tool belt, okay? All right, great. Now for the fun part, for the math nerd in us, we want to go under the hood and how this whole thing works, the least squares regression, or just regression, how it works. We start with the definition. Let me remember it first. Okay, so the idea is, given a set of observations, when I say an observation, that means a pair of data, x and y, or x, y, and z data. So data that is full, independent and dependent variable. Given a set of data points or observations and a model curve with unknown parameters. Why I insist on that, the model curve is something that you choose. You choose to do a straight line. A straight line is a model of the data, okay? You choose to put a cubic. That's your model. My model for the data is that it follows a cubic or a parabola or a sinusoid, okay? That's your choice. How you determine that from intuition and experience, okay? Right now, I'll give you those models, but eventually you will know what you need to put to model those data. Okay? It comes to you with time. So, but you're given a model curve with the unknown parameters that are always the coefficients. Because in this case, you have x and y values, You're looking for for the coefficients that would make the model curve capture the trend of the data. We will define what we mean by that. Okay. We will find those parameters such that, and this is going to be a mouthful, probably too much for words, but once you write it mathematically, it becomes clearer, hopefully. So we want to, if we are given a set of data and a model curve with unknown parameters, those are the coefficients in the model curve, find those parameters, the unknown parameters, such that the sum of the squares of the error between the model curve and the observations is minimum. So I'm going to draw this model curve over here. Okay, I'm going to draw this model curve over here. These vertical bars are the error between the true data or the observed data and my model. I'm going to make this curve, I'm going to adjust it so as to minimize the sum of the square of all of those errors. That's how we get that curve. So we're going to add all of those errors, and we're going to minimize them and find the conditions for this curve to minimize those errors. That's the best we could do. With interpolation, our conditions were go through each and every point. That's simple. Here, no, I don't want to go through each and every point. Because I can't. Maybe I have 1,000 data points. What do you want me to do? 999 ordered polynomial? I could put maybe a straight line with 1,000 data points. But I'm going to adjust that straight line to minimize the error across all of those points. Okay? So think of this as it's trying to adjust it, kind of level it, just to minimize the total error committed in modeling the data. Okay. We will start with least squares regression to a straight line with a very simple example. Very simple example so that we get the machinery working, and then we'll generalize. Okay? Very inductive approach. Okay. So suppose you have these input data, and I chose 3 data points on purpose, because if I chose 2, of course I can put a straight line between 2 points. It's going to pass through those 2 points. So, that's a degenerate case. So I chose 3 data points because that's the simplest case where I can't fit a straight line because those 3 points are not aligned together. So those are the input data. They're given to you as x1, y1, x2, y2, and x3, y3. So again, think of this as femur length and a person's height. Okay. Next, I want to draw a curve, a model curve. In this case, I want to put a straight line. And I don't know if it looks like this. I'm just kind of drawing it. I don't know exactly what the slope and intercept are. I'm just drawing it for illustration. But I know I want to draw a straight line to model those data. And that model curve for the straight line is a0 plus a1x. Now, by definition, our objective is to find a0 and a1 so that we get the best trend of the data. So our objective is still to find the coefficients like interpolation, exactly the same. But the conditions are different. Now, if I were to take this model curve and evaluate it at the input data, I'm going to get, in general, a different number, right? Because this curve doesn't go through the data. In interpolation, the curve will go through each data point. So if you evaluate the interpolation curve at the input data point, you're going to get the same value as the input. We did that test when we did interpolation. With regression, that's not a guarantee. So if I were to evaluate this regression curve at the input x1, it's not going to return y1. It's going to return something else, right? So this is y1. It's going to return something else because it could be higher or lower. Doesn't matter. And I will call that f1. Now, what is f1? I now have the formula. f1 is a1 x1 plus a0. I'm just simply evaluating my model at the input data. If I go to x2, I get the same thing. I don't get the original input data point. I get something else. I'll call it f2. That's my model data point. And it's a1 x2 because still the model curve is the same. It's a0 plus a1x. Except now it's evaluated at x2. So I get a1 x2 plus a0. It's great if you do this by hand. You go home and just do it by hand so that it sinks in your head. And finally, at x3, I get another number, f3. It's also a1 x3 plus a0. Now, those red points are the model prediction of the input data. Okay? The blue points are the input data, and the y values of the input points are the input data. The red values are the model predictions at the input data. So I didn't change x. I still evaluated my model at the same inputs, but it gave me a different value. Okay? All right, so let's now shrink this a little bit, clean it up. All right, so I have this now. Now, the difference between these points, I'm going to call that an error. Why? Because my model is giving me a prediction different than my input data. So that's an error, right? Now, why would I want a model? Because the model gives me a single formula to capture the trend of millions of data points potentially, instead of having to go through the data points and kind of think and reason about them. And I cannot do interpolation on data point that looks like scatter like this, or like the height versus femur data. You can't do interpolation there. You have to do a regression on it. But the benefit of the model curve gives me a single formula that I can summarize all the data with, or represent the data with. The difference between my model value and the input value is an error. Agreed? It is an error. It is actually a true error, because I know this is the truth, and I know this is the approximation or the model. So this is a true error. f1 minus y1 is the error committed at this point. At the other point, I have f2 minus y2, and at the other point is f3 minus y3. I have 3 errors now for these 3 data points. If I have 1,000, I'll have 1,000 errors, obviously. Okay, good. Now the idea is find a0 and a1 such that the total error between f1 and y1, f2, y2, f3, y3 is a minimum. So now I want to adjust that line so as to minimize the distance between the line and the points. You see the challenge here? I want to adjust that line, the slope and the intercept, just kind of move it just a little bit, to minimize the total error between all of those points. Now, a common measure of the total error is simply the L2 norm, or the Pythagorean norm of the error. That's the simplest measure of an error. If you think of these 3 errors as a vector, E1, E2, E3, what is the length of that vector? It's the square root of E1 squared plus E2 squared plus E3 squared, right? And so I define an error. We call it S, colloquially. That's kind of standard nomenclature in the literature. And the sum of all of those errors squared is given by this. So that's essentially related to the L2 norm of the error vector. Okay? Now, what is E1 and E2 and E3? I'm going to express them back in terms of y1 minus f1, y2 minus f2, y3 minus f3. And I don't care about the sign, f1 minus y1 or y1 minus f1, because it's squared. It doesn't matter which one you take first. You don't need an absolute value. It doesn't matter. It's irrelevant. Now, here's the kicker. However, f is a1x plus a0. So f1 is a1 x1. Remember, f1 was a1 x1 plus a0. f2 was a1 x2 plus a0, and so on. So I still need to tie this to the coefficients, and this is where the coefficients come in. So now go ahead and replace f1, f2, and f3 in this S. Okay? So use this to bring in a1, a2, and a1 and a0 into this equation. Simple substitution. F1, A1, X1 plus A0, F2, A1, X2 plus A0, and so on. Yes, so Y1, F1, Y1. Yeah. Nope. There's no A3. There's no A2, right? It's one model curve, right? That's the trick. Remember, the model curve has the same A1 and A0. It's just evaluated at different x values, okay? All right. Perfect. Yep, perfect. Oh. You got it. Okay. Yep, you got it. Okay. That's a common mistake. Okay. So common mistake is that you think that F2 has different coefficient, A2 and A3 and whatnot. No. Fi at any point, A1 and A0 are fixed, are the same in any one of those terms. The only thing that's changing is where it's evaluated at, or the x value. Okay? So if you did this right, you should get something like this. For F1, you have A1 x1 minus A0. For F2, plus A0, so with the negative sign. And for F2, you have A1 x2 plus A0. For F3, you're just simply putting F1, F2, F3 over here. Okay? Okay. All right, so we're still at the same idea. We want to find A1 and A0 such that the total error between Fi and Yi is a minimum. Now, we have an expression for the total error. We have an expression for the total error. Okay? How do I find its minimum? You remember your calculus? Okay, how do you find Ashton? Yeah.
Second derivative test, concavity or?
So that gives you the concavity, is if it's going to help you find if it's a minimum or a maximum. But what is the other test? So when is a function at a minimum or a maximum? Just f of x. When the first derivative is 0. Okay? But that's for a function of one variable. How many variables do we have here? Okay? So we have victory sign, 2, 2, 3, 2. Do we have 4? Do we get 4? 2, 2. Okay, why 3? Okay, why 2? Aaron. Yeah. Okay. So what is unknown in this formula? What is not known in this formula? A1 and A0 are unknown. Everything else is known. X1 and Y1, by definition, I said you're given those. So there's just going to be numbers. So this is a function with two variables in it, A0 and A1, A0 and A1. Okay? So the first derivative test still applies in 2 dimensions. Okay? You just have to take the derivative with respect to both of those unknowns. So with a single independent variable f of x, that function is at a minimum or a maximum when its first derivative with respect to x is 0. Here you have 2 independent variables, a0 and a1. It's still true that that function is at a minimum or a maximum when its derivative with respect to both of those variables independently, its first derivative is also 0. So s is a minimum, or an extremum specifically, if both of those conditions are met. If the derivative with respect to a0 is 0, and the derivative of s with respect to a1 is also 0. Both of these conditions need to be met at the same time. So the curve has to reach an extremum, maximum or a minimum. Now, in this case, we know it's going to be a minimum for reasons beyond what I want to discuss here. We know that always with least squares regression, if you do this, you will always get a minimum, guaranteed. You're not going to get a maximum. You'll always get a minimum because of the nature of the squares. We're not even going to talk about that. I have some material that I uploaded on Canvas that explain why you get a minimum. So we have to do a second derivative test and whatnot. Okay, so I put it here more accurately. These are the conditions for an extremum. A minimum is only guaranteed when the second derivative test applies. For regression, this is always true. So for least squares regression, this is always true. You get a minimum. Okay, so now find me those equations. Oh, you already did that. All right, so now write it so deduce the system of equations and write it in matrix form. And solve it and give me the... No. You did this and you can do the rest in a second. It takes 5 minutes. Well, you brought this to yourself, right? You solved it very quickly, so... Okay, so do those derivatives. Remember, you're differentiating with respect to a naught, and you're differentiating. So when you differentiate with respect to a0, everything else treated as a constant. When you're differentiating with respect to a1, everything else is a constant. And the derivative of un prime in general is n times u prime times u to the n minus 1, okay? If you're stuck a little bit, let me know. Come and help. Yes. Mm-hmm. Oh, excuse me. Sorry.
So I'm like really tired because I just got back from San Diego. So
No, don't worry.
we're just like we're doing partial derivative of the u to the n, that one. Or what?
No. This is a general reminder of the formula
Yeah, okay.
for the derivative of a power.
Oh,
Because
yeah,
up
yeah,
there you have squares.
Uh-huh.
So how do we differentiate a square? It's n times what's under the square times the thing. Yeah, exactly. Yeah. But you're doing the partials. Yeah. So ds by dA naught. So you have squares there. So it's gonna be 2 times the derivative of that with respect to a naught times that thing to the power 1 plus the same thing on the other, same thing on the other. Okay.
Yeah, thank you.
Okay. Yeah. So this is just to remind you of how to differentiate a power, because you have squares over here. You have these things in parentheses with squares. So
The constant disappears. Yeah.
okay. Is this S? What?
That's S.
S. Oh, yeah. So don't forget the squares then, right? You have squares. Okay? Keep working on it. So at least I want you to work on this activity so that the next activity we can skip and you can do it at home. Yeah, it looks beautiful. Yeah, so you don't need you don't need the squares there. Okay, so now take this and
Put it in matrix.
yes, you got it. And then solve it and okay, at least if you can put it in matrix form, that's great. Okay? Okay. So I think you might have a little mistake here. So you're differentiating with respect to A1. right? So, so it's going to be x1, right? Okay, yeah, yeah. I like how you're keeping the color track of the colors. That's really smart. How are we doing here? In trouble? Okay, Alexis.
I don't know. It's been a couple of years.
Okay, no, you got it.
Okay, yeah, that's.
Yep.
okay, well,
Now, okay, now think about this. Now this is equal to 0.
Yes,
You have two equations, two unknowns. If they're linear, then put them in matrix form.
perfect.
Okay? Let's see. Okay. Need help?
I got stuck. I did not do good in calc, so.
Okay. So you need to work on those derivatives then.
Yeah.
Okay, so you got the first one,
Yeah.
2 times the derivative to the power n minus 1. You still need to differentiate what's inside the parentheses with respect to a naught. So what's the derivative? So you got you have a negative 1, right?
Like the partial derivatives.
Yeah. Well, forget about. Think of everything else except a0 as a constant. Everything else. So when you're doing the first one with respect to a naught, everything else is a constant. Doesn't matter. Yeah. So their derivatives will be 0, right? Except for things that multiply a naught, right? So here, when you differentiate, so the derivative of this thing squared is 2 times the derivative of it with respect to a naught, right? Negative 1, agreed, yep. And the parentheses to the power 1, right? Same thing for the other ones as well. Now when you go to a1, but then you have an x1, right? Yeah, yeah.
Thank you.
Okay. Okay. So we'll work with you on the derivatives in the help sessions or in office hours. But this is the answer you should get. You take each term, you differentiate each term using the power rule for derivatives, n times u prime times un minus 1. Remember what you're differentiating against. Here you're differentiating against a naught, so you're going to pick up a negative 1 from each term. Here you're differentiating with respect to x1, to a1, so you're going to pick up a negative x1 with, okay. So let's not forget what we're after. We are after a0 and a1 such that s is minimum. These are the conditions that s is minimum, two equations. And we have two unknowns, a0 and a1. We got a closed system, guys. This is incredible. So we started with something completely like, how are you going to get from the error to the coefficients? This is it. Minimizing the error gives me sufficient conditions, a sufficient number of equations, as many equations as there are coefficients actually in the model. That's what's so great about this method.
Why are they negative? I thought they were positive.
Pardon me?
Why is it negative 2? If we were taking derivatives, why would they be positive?
But you pick up a negative 1 from the coefficient of a0 and the coefficient of a1, right? Because you're differentiating inside the parentheses as well. Okay. So now you rearrange that. You look at it. It's a complex expression, but you know it's just a bunch of terms. And all what matters here is that the coefficients show up linearly. Because that tells me this is a linear system of equations in those coefficients, which is great news. You rearrange things, you put the unknowns on the left-hand side, you put what you know on the right-hand side, you get two equations with two unknowns. You can solve those for a1 and a0. Okay, you move the x, y1, etc. You can solve this exactly, actually, and you get your regression line. Okay? That's it. That's what regression is. In whatever the model curve, I could put elephants in the model curve. You follow this procedure, you're going to get these equations. Later we're going to call these equations the normal equations. Okay? But there's nothing normal about them. They can be very complicated. But that's the methodology. Okay? So now we're going to generalize it. Now instead of just 3 data points, and this will actually be easier because instead of all of these terms, you're going to have summations. We're going to do it for an arbitrary number of points. So instead of 3 points, I'm going to take an arbitrary number of points. I'm going to follow the same procedure, x1, x2, xn, yn. N number of points, n observations. x1, y1, x2, y2, x3, y3. Okay? So n observations. I'm going to put a model curve between them of the form a0 plus a1x. Now, obviously, this cannot be interpolation because I have more points than what the straight line can go through, okay? So it's definitely regression. And we do the same procedure. We define F1, F2, F3, and so on. These are the model predictions. The error, the difference between all of those are going to be the errors. So you have n errors. And then you define your total error as the sum of the square of all of those errors. So in the example we did, we had 3. Now we have n. So what? Okay. But what's clean about this is that, okay, so I can write it in this way, but I can generalize it and just write it as a summation over all the input points. So y1 minus f1 squared plus y2 minus f2 squared and so on. I can just put it in a summation of yi minus fi squared. F is the model. Y is the input data, the dependent input data, the value of the dependent variable in the input data. And I is the index of the point, first point, second point, third point, etc. Okay, don't confuse that with input. That's not, I is not input here. This is the point 1, point 2, point 3. Now my fi is still a1 xi plus a0. I have one model curve, one set of coefficients applied at each one of those points. So you substitute, just like we did previously, except previously you had to do it 3 times. Now you do it under a summation. But you do have an index I to keep track of. So now you have yi minus a1 xi minus a0 squared. Same thing as you did by hand just a minute ago, except now that it's in a summation. Still, s is minimum if and only if its derivatives with respect to the unknowns is 0 concurrently. So derivative with respect to a0, derivative with respect to a1 is 0. You still have, could be a very lengthy summation. Could have hundreds of thousands of terms in it. But you still have only 2 unknowns, a0 and a1. Okay? Now, this you will do at home. I told you I'm going to kind of skip things a little bit. And it's cleaner this way when you have the summation. You don't have to do it 3 times or 6 times. You just have to do it 2 times. And it's cleaner to see how the derivative works. So this is what you get for regression to a straight line. You get minus 2 times that summation and minus 2 times that summation. But note that there's a xi over here. So that's the derivative with a1. You're going to pick up an x1 and x2 and x3, etc. So if you take this and apply it to the problem we did just now with 3 points, so I goes from 1 to 3, you're going to get exactly the same answer you did by hand. Okay? Just abstracting things a little cleaner. Now this is very clear that these are 2 equations with 2 unknowns. Red, ones in red, a0 and a1. Despite the summation doesn't add more unknowns. It just adds more terms that contain the same unknowns. So these are 2 equations with 2 unknowns. Okay, so now let's split the summation for simplicity and to write it in matrix form. So I'm going to split the summation and get rid of the minus 2 and work with the sign a little bit. So I got rid of the minus 2 and I have summation of yi minus a1 summation of xi minus summation of a0 on the first equation. And the second one, I have summation of xi by I, right, minus a1 summation of xi squared, because xi, minus a0 summation of xi. Why does a0 come out of the sum and a1? Because they're not dependent on the point. They're the same for each and every point. So they're not under the index summation, okay? a0 and a1, they're the same everywhere across all of those data points. So they can come out of these summations. Okay. So if I clean this up a little bit, notice here that summation of a0 is actually a0 times n, because that's a0 summation of 1 n times, going from 1 to n. So you're adding 1 n times, or you're adding a0 as many as there are data points. So a0 plus a0 plus a0 plus a0. So you're going to get this a0 times n. Just be careful of that. So when I give you a problem with a trick like this, just be careful of how this converts to a0 times n. Okay? Now I ask you to write this. I normally ask you to write this in in matrix form. Again, you're going to do that at home. And what I would do is rearrange the terms. So n times a, now I'm just cleaning things up. I move what I know to the right-hand side. And so I grab a negative sign, then I multiply everything by -1. So everything now is plus and positive coefficients. And then I have my unknowns in red and the coefficients in black. And I can start seeing the structure of the matrix. And I get this for my system of linear equations. The first equation is n times a naught plus a1 times summation of xi equals summation of yi. And summation of xi, a times a naught, plus a1 summation of xi squared is summation xi yi. Look at the beauty and the structure of this matrix. You have this symmetry here, summation xi, summation xi. If you go n to x and then x to x squared, and that pattern will repeat. You will see as we go to higher order polynomials, you're going to get x cubed, x to the fourth, and so on and so forth. And notice here also, summation of yi, summation xi, yi, some beautiful symmetries, properties of regression to a straight line. And this is a system of linear equations. We know how to solve this. You can throw this in numpy.linalgebra.solve, okay? And you will get exactly the same answer we got from Polyfit. But that's what Polyfit is doing. So Polyfit gets the degree. It says, oh, I am doing a regression to a straight line. What are my input data points? Build this matrix. I have 50 data points. I'm going to put 50 here. I'm going to sum up all the xi values, sum up all the xi values, sum up all xi squared, and do this and solve the system of equations and give back the coefficients. That's what Polyfit is doing. No mystery. Whoever designed Polyfit, okay, didn't take the course with me, but knows how to do this, right? And now you know as well. Now, in this case, we have an analytical solution. I hardly worry about this analytical solution. But then if you want to kind of do the exercise by hand for the input data that we had for the femur length and the height, and you can do summation xi, summation yi. If you're kind of doing it by hand, you know, you would get, this is a proof that you get the same answer. And those are the coefficients we got from Polyfit. They're exactly obtained here from these summations. If you punch in those numbers, you can work this at home. Please do. Just kind of see how the mechanics work. It's tedious, but you know, it's not that many points. You can put them in Excel if you want and evaluate the sum, because you know, in that formula up there, you have sum xi squared, right? So I have here sum of xi, sum of yi, sum of xi squared, and sum of xi yi, which are needed in those formulas up there. Okay, the next one you're also going to do at home is the Python. We did it with Polyfit, and what I will recommend you always do is use Polyfit when you can. There are cases where you have to manually program this, and we will get to that point where Polyfit cannot do it for you. So we will have to program it ourselves. We will talk about that later, but this, you know how to program this system of equations already, a system of equations from, you know, linear solvers, right? So if you're doing Python, you don't want to do Polyfit, you can do it yourself. And to get all of the terms in the coefficient matrix, you can use things from NumPy. NumPy.sum will give you the sum of an array. So you could do NumPy.sum xi, that gives you summation of xi. NumPy.sum of xi squared, that gives you summation xi squared. NumPy.sum xi times yi, so it takes two arrays, multiplies them, and sums them up. So you have all the features needed. You do this at home. I'm not going to spend time doing it here. It's kind of an obvious exercise. You know how to build an array already and all of this. So, and then you use numpy.linalgebra.solve, and you get the solution, okay? And in your Jupyter notebook with gaps, I have this already pre-programmed for you. The challenge here, though, is that you don't have polyval. Okay, so you get the coefficients from this solution, but you still have to write a routine to compute the straight line, to evaluate the model, right? And so you would have to create a Python routine that does that, and you can simply create it. Okay, you have the solution from linalgebra solve, a0 and a1, and you define your model a as a function of x, and you just return the straight line. Polyval is doing this for you. It's actually doing all of this for you. It takes the array of coefficients and evaluates it at a value x. Okay? Either one works. They will give you exactly the same answer. If you're So I leave this for you to do at home, but I just want to show you here. Regression to a straight line, this is the system here. Okay, so you just follow the slides and the code, and you'll get all of these as the same answers. So you can experiment with that on your own time, please. Okay? Is it necessary to know how to do this? I think so, because there will be cases later where Polyfit is not going to work. The challenge with Polyfit, it has to work with a full polynomial, a0 plus a1x, or a0 plus a1x plus a2x squared, or a0 plus a1x plus a2x squared plus a3x cubed. But what if I tell you I want a0 plus a3x cubed? Polyfit cannot do that. You know what? See what I did? I put a0 and a3x cubed. I dropped the other two coefficients. It cannot do that, Polyfit. It has to have a full polynomial. Okay? So then in those cases, you have to derive the equations by hand. That's why we did this exercise. My son tells me, why can't I use a calculator? I said, because you need to know how to think. If you rely on a calculator or a GPT or all of this, what are you going to be? An empty vessel. Even if there are tools that do this for you, you need to know how to do them. Then use the tool. I use those tools all the time. But boy, can I spot a mistake when it makes a mistake. Because I know how to do it. And that's why we're trying to do here. Okay? Yes, there are tools that do this for you, but what's behind the tools? The person who created those tools was sitting in your chair here and learned how to do it themselves. Okay? So this approach will be important if you're doing something that breaks Polyfit. The weakness of Polyfit is that it needs a full polynomial. If you have a model that doesn't look like a full polynomial, you can't do that with Polyfit. There's another option we will learn later called curve fit, okay, that could work with all sorts of models, but it has its weaknesses as well, that other one. Okay, so each one of those approaches has its own place, okay? All right, so here's the coding here. Sorry, I wish like I said, I want to accelerate this discussion a little bit. So some of these activities, I really encourage you to do them at home in the help sessions. Put the time, yes?
Are any of them in the videos from last year?
Yes, that's actually great. Thank you for pointing that out. So if you go back to last year, that's a great point. Actually, yes, go to last year's lecture and you can see the details. It's just a 15-minute discussion. Okay, but I'd rather spend those 15 minutes this year to push you to nonlinear regression because that's what I want to cover. That's really the harder problem, okay? But if we continue at the pace we were working at, we won't be able to do nonlinear regression. That's a great point. Thank you for that. Okay. All right. So let's see where we're at. You do this with the data set. Okay. Now, I want to introduce the idea of the normal equations. And this is the first, the governing equations of regression. The governing equations of regression, what do I mean by that? It's kind of a vague statement, governing equations of regression. It's the equations that govern the unknown parameters of the model curve. Those equations, what do? They minimize the error, or the sum of the square of the errors. They minimize the error between the model curve and the input data. Keep that in mind. How are we building that curve? By minimizing the error between that curve and the input data. We capture that trend. Okay? The equations that govern those parameters are called the normal equations. So ds by dA naught equals 0 and ds by dA1 equals 0. Those give you the normal equations. These are the normal equations. Whether the regression is linear or nonlinear, they're still called the normal equations. Okay? They're still called the normal equations. Keep that in mind. What are the normal equations? They are the equations that govern the parameters of a regression model and minimize the square of the error. I have a better definition here. They are the equations that govern the parameters of least squares regression. In other words, the normal equations are obtained by setting equal to 0 the partial derivatives of the sum of the squared errors to obtain the least squares equations. Okay? All right, so I want to get started on error analysis. We have 10 minutes. I would normally give you a break after the normal equations, but we have to keep going. Okay. Let's see. Okay, we're going to start with the definition of a standard deviation. Okay, what is standard deviation? You didn't take statistics, so last spring I asked everyone about standard deviation. They had statistics, so it was fair game. But I know some of you, they learn about it potentially in high school. So what do you think when you hear standard deviation?
It's like the average distance away from the average.
Wow, that is pretty accurate. The average distance from the average. Okay. What else do you think about standard deviation? That's exactly right. That's exactly right, and it's a very good definition. So yeah, what do you think of standard deviation?
That average dissipates as you get further away from, I'm thinking of a.
Oh, you're saying of a bell curve, and but what is the standard deviation? When we say this data has a standard deviation of 10%, and that data has standard deviation of 50, like in the unit, in the measured unit, whatever unit that is. And so what does that mean? Yeah, and why is it important? Okay, well, I want to explain that to you. If you've learned it, this will be a different way of explaining it to you. If you haven't, I think it's a great way to explain. I never understood what the heck standard deviation was until I started putting those lectures together. And notice what I did here. I said error analysis, and the first item under error analysis is standard deviation. Because my interpretation of standard deviation is it is actually an error in the data. And that error measures the average error from the mean of the data, like your colleague just said. Okay, so let's consider a bunch of data points. Again, we're going to go back to the femur length and person's height. The data looks like this. Okay, just a scatter. Femur length on the x-axis, person's height on the y-axis. Okay. Now, what basic metric would you use to describe these data or any other data? If I give you, I came in and just gave you data, and you work for the governor and you want to report some statistics to the public. According to these data, the is such and such. What is that metric that you use? It's a very simple metric. So let me help you out. So suppose you want to get your finances in order and you want to start budgeting, okay, like a champ, okay, and then your first item of business is dining out, which is obviously nobody dines out, right? And so your budget for dining out, what do you set for next month? Let's say you have data for the last year. One month you spent $50, the other month you spent $70, one month you spent $15. What is your best guess for next month's budget for dining out? Okay. Okay. So like the average. Okay, what else? You don't know anything else. You just have those numbers. Every month you have, this is what you spent last year on your credit card. You track that category and you say, okay, I spent in January, we spent $50, then 70, then 60, then 35. What is your best guess for next month? It's going to be the mean. In the absence of any other information, the best description of a data is its average. That's the simplest description of information, is its mean value, its average. I agree. So the average or mean value is the simplest metric you can get or you can set for a data set. And it's simply defined as the sum of the values, the y values obviously. So if you were plotting dining budget or dining spending versus month of year, you'd have in January, you'd have $50, in February, you'd have 60, etc. You sum up those numbers, 50, 60, etc., and you divide them by the number of months, right? So 12 values over 12 months gives you an average. Same thing here, just get the data. We call that y bar for average, okay, y bar. Okay? So for example, for these data, the average height of a person in these data is 167.8 centimeters. That's suspiciously almost my height. Okay, so the mean value then would be just a fixed value across all of the x data, okay? So the mean value, in this case, is this line. Now the mean value, just visually looking at it, okay, not the median. The median splits the data in half, we will learn in statistics. The mean value, the average value, splits the data with values above it and below it. It's not in the middle of the data. Don't say it's in the middle of the data. The mean will be skewed typically if you have a lot of large values, or one very, very large value and a lot of small values. It will drag the mean all the way to the larger value. It doesn't split the data in the middle, not at all, okay? If it does here, it's just a coincidence. But the mean splits the data between data above the mean and data below the mean, or to the left or to the right of the mean, whatever, however you want to think about it, okay? Now, we call this the spread of the data with respect to the mean. Okay, so now you look at the mean. Oh, you see the data is spread around the mean. Now, each data point falls a distance from the mean. And that distance is the true data point minus the mean value, right? Like we did with the regression, the model value minus the value, okay? So if you call this yi minus y bar, this would be the distance between each data point and the mean value. Okay. Now the aggregate distance of all points from the mean can be defined as the sum of the square of all of those distances. Okay? Now why I'm using the mean as my reference value? Because in the absence of anything else, it is the best descriptor of a set of data. So if I'm treating the mean as a representation of the data, the distance of those data from the mean act like an error with respect to the mean, to measure the spread of the data from the mean value. The sum of all of those, just like we did before, the sum of all of those, we will call it S sub t. Again, I don't know why they came up with this nomenclature, but I'm trying to adopt common nomenclature in statistics. We will see this again in stats. It's simply the sum of all of those distances squared. So you take each data point, the mean value is a constant, so y bar is a constant value. Yi minus y bar gives you a distance from the mean. You square that and you sum them all up. That gives you a measure of the total distance, okay, of the total distance. Okay, now we can compute an average distance from the mean value. Give it to me before you go. What do you think the average distance is going to be? We have the total distance, and I have n points. Okay. What is an average distance from the mean? Average distance, average. You have n points. Yes? Divided by n? Divided by n? Divided by n? Yeah, divided by n. Okay. You're correct, but a little wrong. It's actually divided by n minus 1. We will learn why in statistics. This is statistics world because this is a sample property, not a population property. Okay, we will learn the difference. If it's a population, you divide by n. If it's a sample of the population, you divide by n minus 1 for bias reasons. We will explain that hopefully in statistics. Okay. Now this average distance, sum of yi minus y bar squared over n minus 1, this is still an average distance. We call that S sub y squared, and we call that the sample variance. That's the variance of the data. Okay? Bear with me 1 second. And then, if you think of this, this is, the units of this are in the square of the response variable. If you want to the average distance in the units of the original variable, you just have to take the square root. When you take the square root, you get the standard deviation. When you get to the square root, you get the standard deviation. Okay, we'll review this. You'll review it to remember the definition. But I think of the standard deviation as the average error committed in the data if you use the mean as the representation of the data. So if you were to use the mean to represent the data, what is the average error committed in all of the spread of the data? What that tells you, if that average error is small, it means your data is all clustered around the mean. So therefore, if the standard deviation is small, all the data is clustered around the mean. If the standard deviation is large, the data has a lot of error with respect to the mean, and they're spread wildly away from the mean value. Okay? We will review this concept on Thursday and pick it up from there and do the same for regression. Okay? Thank you. Godspeed.